Hello everyone, this is the day 2 of verifying trig identities. I decided to go over, for the second piece of homework that goes up to about 25, I decided to go over number 16 and 22. 22 I will do in two different ways to demonstrate the different approaches to verifying an identity. These definitely look more daunting than maybe the beginning verifying identities that we had at the beginning of day 1. But ultimately, if we stick to our guidelines and trig and algebra skills, these are actually quite manageable. And hopefully I'll demonstrate that here. So for 16, if you look at this, you always are looking for which side to work on. More complicated side is the side we want to work on. And obviously the left-hand side is way more complicated than the right-hand side. If you'd wanted, for instance, to try to turn 1 into all that mess on the left, you could go in an infinite amount of directions. So obviously in this one, we're going to work on the left. And when I look at this, and again, I'm verbally trying to demonstrate my thinking and approach to trying to verify this, my first thought is that I see squared terms, so Pythagorean identity is going to come into mind, particularly with 1 plus tan squared. And when I look at 1 plus tan squared, and again, this is like the thinking ahead, should I go this route? I mean, we could just try it, but I think the more you get comfortable with this, the thinking about it and thinking what will happen if I do this step is a really important aspect of the problem solving approach to this. So 1 plus tan squared, when I look at that, I know if I look at my Pythagorean identities, that's secant squared. So I think, okay, if I make that secant squared, how is that going to help me in the future on the next line? And you see you have a cosine squared there, and we know cosine and secant are related by being reciprocals, so that lends itself to a promising step. So that's what I'm going to go with. I'm going to take the 1 plus tan squared, and I'm going to use the Pythagorean theorem, substitute in, that equals secant squared theta. And now when we look at that, you see that both the cosine is squared and the secant is squared, and they are reciprocals of each other. Well, if I have reciprocals of each other and I'm multiplying, they equal 1. So this should equal 1. And you could go straight to 1 here. You could go straight to 1. And in my opinion, as a teacher, that's sufficient work for full credit. But let me try to more explicitly demonstrate why this would equal 1. So secant, when we look at our reciprocal identity, secant in the numerator is equal to cosine in the denominator. Therefore, if I have secant squared in the numerator, that would mean I have cosine squared in the denominator, just as if I had secant in the numerator, that would be cosine in the denominator. Secant squared in the numerator is going to be cosine squared in the denominator. And then this explicitly demonstrates, if you didn't see it before, that cosine squared over cosine squared cancel, and we get 1. All right, for number 22, I'm going to demonstrate this in two different ways. The first way I'm going to demonstrate by working on the left-hand side, and then the second time after this example, I'm going to demonstrate how to do this verifying identity by working on the right-hand side. Now, this gets into a more dynamic, interesting conversation about what's the more complicated side. And on 16, it was quite obvious that the left-hand side was more complicated. So here, it's a little more nuance of discussion, because if we look at the left-hand side and you say, is that more complicated? You go, well, what would I have to do to the left-hand side to make it look like the right-hand side? Well, that's a fraction, a one-term fraction. It has terms within it, but it's a fraction, so it's just ultimately altogether one term. And you go, okay, if I want to split one term into two terms, because we have two terms on the right-hand side, that's actually making an expression more complicated, right? It's taking, when we simplify, we're taking actually two terms, three terms, etc., getting like denominators and combining them into one. That's simplifying it. So it's not, like, I guess, mathematically accurate to say going the left-hand side to the right-hand side is simplifying it. But if we use our certain algebra skills, we can very easily get from the left-hand side to the right-hand side. And what do I mean by that? And this is hopefully what you recognize when you start seeing something like this, where you have, for instance, like a squared term over a non-squared term, we can break this up into two fractions. And this may not be obvious that it will get us to where we want to go off the bat, but nonetheless, we could do it this way, where we have cotangent of t over cosecant t, and then we have cotangent t over 1. Now, as I do this step, right away in my head, I am seeing there might be actually another way to do this. So in fact, I'm going to do this 3 ways. But I'm going to continue with this method. So when we get here, we don't have square terms anymore. So my thought is then turning everything in terms of sine and cosine. So let's see what happens here. So if I go cotangent in the numerator here, I'm going to turn cotangent into cosine t over sine t. That is our quotient identity. And then I'm going to go here, cosecant, I'm going to turn that into 1 over sine t. Times over here, cosine t over sine t. That's over 1. Okay, so now, I'm going to shrink this down a little bit. At least try. There we go, you do it like that. And now I'm going to try to deal with this whole mess here. Okay, so I don't see any cross-canceling, obviously, but this, I can multiply the sign up, and let's see what happens. So if I'm multiplying by the reciprocal, because when you're dividing by something, you multiply by the reciprocal. The reciprocal of 1 over sine is sine. So now I have everything lined up, right? So this is in the numerator here. If you look here, I could go with sine over sine, those cancel, and now I have cosine squared t. I took this term, multiplied it by this term, and that's cosine squared, and then all this down here is 1, and lining up right here, sine is gone, there was a 1 there, and a sine t, we have over sine. Now, it doesn't seem like this has gotten us that far, but this actually alludes us to the fact that we could break up it into 2 terms. Why would we want the numerator based on cosine squared? Now, why would we want to do that? Well, look at where we want to go. We want to separate into 2 terms. So, again, I'm just kind of exploring a way to go about this and see where it gets me. And now I've gotten to the point where it's like, well, those steps got my terms into cosine and sines, which is much easier to work with cotangents and cosecants. But now I got to figure out how to break this up into 2 terms. And so I see that cosine squared, and I know the Pythagorean identity gives me 1 minus sine squared t over sine t. And now I go, yes, I can break that up into 2 terms by subtraction. So if I do that, the first term would be 1 over sine t. Note that would be just that over that, minus sine squared over sine. And now I've broken up into 2 terms, 1 term, 2 term, which models what I have over here. Well, let's see what we want to get. From this, we want to get a cosecant minus a sine. Well, this is our positive term, cosecant. Well, over here, this is our positive term. Well, what again does, hold on, I'm just trying to keep my space. What does 1 over sine equal? Well, it equals cosecant. So I got my first term. Now that second term I need to turn into sine. Well, that's what it equals because I have sine squared over sine. One of them will cancel, and I'm left with sine t. So ultimately, it probably wasn't the most efficient method, but when I stuck to my guidelines and worked through it, ultimately I came to a point where I could have a better realization of what I needed to do to get there. Okay, doing this problem in a different method. I'm still going to work on the left-hand side, and instead of separating that fraction by multiplication like I did in the last case, I'm going to look at that cotangent squared and go, okay, well, I have a Pythagorean identity, okay? Our Pythagorean identity is 1 plus cotangent squared t equals cosecant squared t. So from this equation, just like we did with cosine squared and sine squared in our first Pythagorean identity, if I solve for cotangent squared t, that would be subtracting over 1. So I have cosine squared t minus 1, and now I have a substitution. I can substitute that in for this right here, and that's what I'm going to do. And 1, I could just try it. But 2, thinking ahead, the reason I see that as very beneficial is because I have a cosecant in the denominator. And if I get that cotangent squared in terms of cosecant, like I did, it's cosecant squared t minus 1, now we can do some separating and canceling. And let's see, when we separate it, we get cosecant squared t, cosecant t, minus 1 over cosecant t. And once we get to here, I've separated into two terms, and I want to get a cosecant minus a sine. So let's see if we can kind of unwrap that or find that from what we have. Well, when I look at this term, I have cosecant squared over cosecant. So those cancel, and that's left with cosecant, which is what I wanted, minus, over here I have a cosecant in the denominator, and I want a sine. This goes back to what we were talking about with reciprocals and the verbalization of how to transform a reciprocal and use a reciprocal identity. Cosecant in the denominator is equal to its reciprocal in the numerator. So in this case, if I have cosecant in the numerator, that would be the same as sine in the numerator. And look at that, we get our identity. We just draw our arrow down. Last way we're going to look at this is working on the right-hand side rather than the left-hand side. So if I work on the right-hand side, this is really more taking something that's complicated and making it more simple, meaning that we're taking two terms and turning it into one. So if we want to do that, the main way that we do that is if we have fractions, we get like denominators, get combine fractions, and then simplify from there. So I'm going to try to get like denominators here. So first off, to make this in terms of being able to work with, I need to get cosecant in terms of sine, which is our guideline of everything in terms of sine and cosine. And we have that. We go, okay, well, that may not be quite obvious how to get where we want to go, but I'm going to continue to work with it. And the way I'm going to work with it is doing exactly like I talked about, by trying to get like denominators, combine, and see what happens. So to get like denominators, I have a denominator of a sine and a denominator of 1, so I obviously have to multiply the denominator 1 by the other. It's like if we have a, 3/4 minus 5. If I want to combine 3/4 and 5, I got to multiply the 5 by the 4 over 4. Same here, I have a sine denominator 1, I got to multiply that second one by sine over sine. So now I have 1 over sine t. I'm going to just do this one step at a time. And now I have sine squared t over sine t. If you want full credit in terms of the way I look at it, you could have skipped that step. But I'm just trying to explicitly make this as clear as possible by going through every step. Now at this point, when we have two terms with like denominators, the simple procedure is combining the numerators, 1 minus sine squared, and keeping the denominator the same. And now I look at that and I go, okay, well, how can I get, just making room for myself, how can I get that to where I want to go up there? Well, I want to get to cotangent squared over cosecant. Well, first off, 1 minus sine squared, I know to be cosine squared. So this is getting me much closer to where I want to go. And this next step may not be parent, it's actually a very elegant and creative way of looking at this. But what I'm going to do, and hopefully the more you practice this within mathematics, you can come up with creative solutions like this. I am thinking, okay, this looks very similar to this up here. But what would I need to do here in order to get this? Well, I have a cosine squared in the numerator, and I want a cotangent squared. Okay, I'm just going to keep in mind, I have this in my mind here, that cotangent squared is equal to cosine squared over sine squared. And then here I have a 1, the cosecant is 1 over sine t. So I want to somehow make this look like that. So how am I going to do that? Well, one thing I could do is say, okay, I want to make this look like this. Well, I already have this right here, but I need this. So if I multiplied this numerator over here by 1 over sine squared t, I now have cosine squared over sine squared, which is exactly the same as what I have over here. But we have to stay consistent with our rules of an expression. If I have an expression here, I don't want to change its value. The only thing I can multiply it by is 1. So if I'm multiplying it by this, I have to, if I want to do this correctly, have to multiply the denominator by the exact same thing. So when I do that, and now we can convert. So looking at this right here is all up here, so we're just looking, I'm going to circle it. In fact, this right here, I want to get it to look like this up here. So cosine squared over sine squared in the numerator right here. Cosine over sine is going to be cotangent, so cosine squared over sine squared is cotangent squared. And then 1 over sine squared right here, here's my large division bar, here's my large division bar. Down here, sine squared, this fraction, just looking in here when I talk about this, sine squared in the denominator is going to be its reciprocal in the numerator, which would be cosecant squared. So that puts a cosecant squared in the numerator, and we have our identity done.